In this video, we're going to talk again about something that is at the heart of this class and of physics in general, which is combined concept problems. So we've already seen how we can have problems in one dimension where you have part that you have to do with calculus, and then a second part where you have to, you just use our regular free fall or our one-dimensional kinematics with constant acceleration to solve. And now that we have 2D motion, we have basically double the types of ways to solve a problem, because we have 1D with constant acceleration, 1D with non-constant acceleration. Now we have 2D with constant acceleration, and now 2D with non-constant acceleration. And you have to know when to apply each type of problem-solving technique. I'm emphasizing this now because as the semester goes on, every module we're learning basically a new problem-solving technique, and there are almost 18 different problem-solving techniques for this entire semester. So a big difficulty with physics, and also one of the wonderful things about it, is being able to learn what physical concept applies to different situations. So being very methodical about your problem solving. A lot of people think physics is just like throw equations at your problem and see what fits and try to find the equation that has all the variables you need. And it is not that at all. That'd be like if you're learning to code and you just sort of like randomly throw lines of code onto the screen. It's never going to make sense. And it's always going to be this big jumble in your head. So you can be just as methodical about problem solving as you are, or as you might be, with coding, in that you want to be very logical. What's my overarching principle? How do I apply it? Which part of the problem does it apply to? And then once you know what concept to apply, you can absolutely right away have those starting steps. For every concept we're learning, I'm telling you, here are the steps that you start this problem with, right? For 2D motion, we've learned that you're going to separate out your x and your y. You're going to start with your x equation if it's constant acceleration, right? And then write out your y equation. You have something to do. You have these steps to follow, but you have to identify it as constant acceleration in 2D first. So what I want is for every combined concept problem for you to label it. And again, the different labels that you might have, you might say 1D constant acceleration, or you might have 2D constant acceleration. These are all ones where you'd be allowed to use those kinematics equations, the ones that were derived assuming constant acceleration. Or you might have 1D non-constant acceleration, or you might have 2D non-constant acceleration. And so for both of these, right at the top, like I said, you can use those kinematics equations. And then for these, you have to use calculus. So you approach them the same, although 2D constant acceleration, you do have to break it into x and y and follow all of those steps. But at least it gives you a starting point, right? So for 1D and 2D constant acceleration, you have separate starting points for those. For 1D and 2D non-constant acceleration, you do calculus. But whenever you're recognizing that that's part of the problem that you're doing, you want to name it, because we're just about to jump into Newton's laws. And then after Newton's laws, we do work kinetic energy, and then we do conservation of energy, and then we do impulse momentum, and then we do conservation of momentum. And all of a sudden, we have so many different problem-solving techniques. And so naming them has been shown to be so helpful in your learning, and one of the hugest benefits of the critical thinking that you can get from a physics course. Okay, so as an example of how 2D combined concept problem might look, you'll be working through one where, for example, you might have a ramp. And then let's say that you have an object that's headed up that ramp. Well, along the ramp, you actually have motion. Yes, it's tilted, so it's not horizontal or vertical, but it doesn't matter. It's still just one dimension, right? It's only moving along a straight line in one dimension. So this is 1D motion along this ramp. And you can tilt your axes on the ramp. You can have your x-axis, just say x points along the ramp. Who cares, right? That's still one dimension. So everything along a ramp might be one-dimensional motion. But let's say then that this guy just goes and flies off the ramp, right? So that's one of the problems that you'll work through. Now, if that happened, let's say this was an angle theta, this will get launched off with some angle theta as well, just like with the ramp, the same angle the ramp made. But now in the air, this motion in the air is now 2D motion. Now on the ramp, you have to read the problem. Maybe it's constant acceleration on the ramp. Maybe the person's hitting the gas pedal and it's speeding up. You'll have to read whether or not this on the ramp is constant or non-constant acceleration and then apply the appropriate things. In the air, this 2D motion, assuming that it's neglecting air resistance, this would be our constant acceleration. Now here's a really important thing to keep in mind. For each part of the problem, you can pick your own axes. So if we had tilted our axes to start with to make this a 1D problem here, and let me just erase that to make it a little bit neater. If we chose our x-axis to be parallel to the ramp for this first part, for the 1D motion, we do not need to keep it tilted for our second part, and we don't want to. For the second part, we just untilt our axes and we'll have our normal XY motion, and then the velocity at the end of our first step, at the end of the ramp, that's along our one dimension, that now becomes our angled launch for this next portion. And so again, you would then have our X and our Y for the second portion of the problem. So you do it the same way that we talked about before with all combined concept problems, where you say, okay, I'm going to first look on the ramp and I'm going to use 1D motion with either constant or non-constant acceleration. You got to read the problem. And I'm going to use that in order to find whatever important thing. A lot of times it might be the velocity headed into the next part. And then you get the velocity headed into your 2D motion part of the problem. And then you're going to use 2D motion with constant acceleration to solve that part. So definitely work on naming these types of combined concept problems, and then putting each part of it and learning to put these concepts together. And let me know if you have any questions as you work through the problem.